Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us through some of the strangest mysteries modern science has yet to solve. But don't worry, you won't need equations or lab goggles. We'll move slowly, like drifting through a star field, pausing at each mystery just long enough to listen to what it's been trying to tell us. Before we set off, you might like to dim the lights or let a small fan hum in the background. Maybe you're already in bed, feeling the quiet rhythm of your own breathing. That's perfect. As you listen, if your mind drifts, let it. The universe is patient and will still be here, unfolding the story together. Science has always been, in some gentle way, a practice of curiosity and humility. For every question we think we've answered, a dozen new ones wait just behind it, blinking softly in the dark. And some of these questions, those that linger just out of reach, seem to invite not just data but imagination. They remind us that knowledge is not only about finding certainty, but also learning how to rest beside the unknown. Over the next 2 hours, we'll explore a constellation of these modern mysteries, a visitor from the stars called Oumuamua that sped past us before we could say hello, faint signals and flickers that some once thought could be messages from other minds, glowing spheres that drift through thunderstorms as if alive, and even the suspicion of a hidden world, a ninth planet wandering in the farthest cold of our solar system. Each of these stories begins with a simple, stubborn fact, something that doesn't fit, a small acceleration where none should exist, a radar echo without a source, a flash of light that appears, then calmly walks through a wall, a handful of distant orbits that refuse to line up the way they should. They are, in a sense, the universe's quiet whispers, little reminders that our understanding, though vast, is still very young. The first of these whispers came in October of 2017, when astronomers in Hawaii noticed a tiny point of light moving far too fast and far too strangely to belong to our solar system. They named it Oumuamua, a Hawaiian word meaning a messenger that comes first from far away. It was small, elongated, like a shard or a sliver of metal, and it spun end over end, catching sunlight in flashes. But what startled scientists wasn't its shape, it was its motion. After slingshotting around the sun, Oumuamua sped up. Just a little, about 17 meters per second faster than gravity alone could explain. It wasn't much, less than a gentle push, but enough to be undeniable. Normally, when comets accelerate, they do so because sunlight warms their icy surfaces, releasing gas and dust that act like a natural jet. But Oumuamua showed no haze, no coma, no visible sign of outgassing. It was as if a sailboat had caught a wind no one else could feel. That odd little push sparked one of the most animated scientific debates in decades. Some proposed that Oumuamua might be a fragment of hydrogen ice, slowly evaporating in a way invisible to our telescopes. Others imagined something even stranger, perhaps a thin, light reflective sheet, a kind of interstellar sail built by someone else. That idea, while not widely accepted, captured imaginations around the world, reminding us how little we truly know about what drifts between the stars. Yet even amid the excitement, a deeper pattern began to emerge. A few small asteroids closer to Earth, quiet, dim, and long familiar, were showing hints of the same subtle acceleration. These objects weren't breaking apart, nor were they glowing with vapor. They were, in the words of one astronomer, dark comets, bodies that may quietly exhale gas too faint to see. If that's true, it suggests Oumuamua might not have been a cosmic anomaly, but part of a hidden class of travellers that move with the softest of breaths. And so, what began as an unsolved puzzle about one strange rock turned into a window into how science really works. We look, we measure, we argue kindly, and we refine our picture of the universe one gentle correction at a time. The answers rarely arrive all at once. They appear like dawn light through fog. dim at first, but steady, growing clearer as patience replaces urgency. Across this series, we'll move through that same rhythm of curiosity. We'll visit the skies above naval ships and pilots who saw things they could not explain. We'll listen to signals that sounded for a heartbeat like an interstellar hello. We'll stand inside a storm and watch a sphere of light drift by, humming softly like a living flame. And we'll end in the outer cold, where a missing planet might be hiding, a ghost world shaping orbits we can't yet see. Each of these mysteries carries two sides, what we know and what we can imagine. But imagination, in science, is not fantasy. It's a bridge. It's what allows us to ask the next question, to build the next instrument, to look again with better eyes. The mysteries we'll explore tonight are not failures of knowledge, they are invitations. They ask us to look closer, to listen longer, and to remember that even in a universe 13 billion years old, discovery still begins with wonder. So let your thoughts slow. Feel the smallness that isn't frightening but freeing, the sense of being part of something wide, still unfolding. The universe does not demand that we solve every riddle tonight. It only asks that we stay curious enough to notice them, patient enough to care, and humble enough to rest alongside them. And as you settle in, perhaps you'll find that mystery, when spoken softly, doesn't keep you awake at all. It helps you drift. Imagine standing on a quiet hillside at dusk, looking up as the first stars appear. Most of them haven't changed since long before there were people to notice them. But in October of 2017, one faint point of light moved differently, too fast, too sharply, to belong to this familiar sky. Astronomers in Hawaii, using the Pan-STARRS telescope, tracked it across the night for only a few brief weeks before it faded into the darkness forever. What they found was not an asteroid from our neighbourhood, and not a comet like those that sketch tales of dust. It was something else, a traveller from another star, the first ever confirmed. They called it Oumuamua, a word from Hawaiian that means a messenger arriving first from afar. From the first measurements, it was clear this messenger did not behave like anything we had seen before. Its path through space wasn't a tidy ellipse that loops back like the planets, but an open curve, a gentle hyperbola, suggesting it had come from somewhere beyond our sun's reach and would never return. Its speed, after leaving the sun, was around 260,000 kilometers per hour, fast enough to escape the solar system for good. At first, scientists thought it was just another rock from space, though perhaps a foreign one. But then came a small, inexplicable detail, the way it accelerated as it left. It wasn't much, just about 17 meters per second faster than what gravity alone could cause. 17 meters per second is the speed of a strong sprint, almost nothing in cosmic terms, yet unmistakable in precise observations. That little extra push meant something was acting on it besides gravity. Normally, such accelerations come from comets, as sunlight warms their icy surfaces, causing frozen gas to burst out in invisible jets that act like miniature thrusters. But Oumuamua had no visible coma, no shimmering veil of vapour. It reflected sunlight without the slightest haze, as if it were completely dry. To telescope cameras, it looked like a dim, bare rock, tumbling through space. So where did the extra push come from? One idea was that it might have released gas so clean and subtle that our instruments couldn't detect it. Another idea, less conventional but more headline-grabbing, came from physicist Avi Loeb at Harvard. Maybe Oumuamua wasn't natural at all. He suggested it could be a kind of light sail, an ultra-thin sheet, perhaps no thicker than a piece of paper, that caught sunlight like a ship catches wind. The concept wasn't random. Humans themselves have tested such sails. A large reflective sheet can use the gentle pressure of sunlight to move, slowly but endlessly through space. If Oumuamua was a fragment of such a sail, it might explain the acceleration, but it would also mean it was made by someone. Most scientists doubted that conclusion, not because it was impossible, but because extraordinary ideas need extraordinary evidence, and there was little time to find any. Within weeks, Oumuamua had faded too far for telescopes to study, carrying its secrets into interstellar darkness. Still, the discussion opened doors to other, quieter explanations. Some researchers proposed that Oumuamua might be made of a fragile kind of ice, perhaps hydrogen or nitrogen, that evaporates without leaving dust. Under sunlight, such material could slowly release gas molecules, producing a push that's invisible to telescopes. Others imagined something more like cosmic sponge, porous and light, capable of absorbing energy and expanding slightly as it warmed, giving itself a tiny boost outward. No single idea fit all the clues perfectly. Each theory solved one problem and created another. Hydrogen ice, for example, would likely evaporate long before reaching us from another star system. A fluffy snowflake-like structure could explain the motion but not its brightness, since Oumuamua reflected more light than a delicate cloud could. The light sail theory accounted for brightness but raised a bigger question. Who built it, and why? Beneath the debate, something gentle but profound emerged. The realization that this small visitor was expanding our imagination of what natural might mean. The line between what nature can make and what intelligence can make may not be as clean as we assume. Space, after all, has had billions of years to experiment. Ice, rock, and sunlight can create designs stranger and more efficient than we might expect. Astronomers continued searching the data, hoping to catch other objects like it. And slowly they did. A few small near-Earth asteroids, objects we'd known for years, showed faint signs of a similar non-gravitational push. They didn't glow, they didn't break apart, but their paths bent ever so slightly from what physics predicted. These became known as dark comets, bodies that might exhale gas in quantities too small for our instruments to notice. If this is true, then Oumuamua might not have been alone, only the first one we were lucky enough to spot. Imagine that. The cosmos could be filled with these silent travellers, each carrying within it a faint breath of its own making, invisible but steady. Like ships moving under a hidden breeze, they travel without tails, without fuss, reminding us how much remains unseen even in the light. For scientists, the mystery of Oumuamua was not just in what it was, but in what it showed us about our limits. Every telescope has its own kind of blindness, every measurement a faint hum of uncertainty. Yet that hum isn't failure, it's the sound of curiosity at work. The unanswered part of a question is what keeps the universe alive in our minds. And somewhere, beyond the reach of our faintest cameras, Oumuamua is still moving, cold, distant, silent. Maybe it's tumbling slowly, flashing sunlight like a heartbeat. Maybe it's alone. Or maybe, somewhere in the endless dark, other messengers drift with it. Other visitors that have passed through countless suns, leaving only a trace of acceleration, a whisper in the equations, a soft reminder that we're not done learning what home means. The night sky, after all, isn't just a map of stars, it's a diary of mysteries written in motion rather than ink. And Oumuamua was one of its rarest entries, a visitor without footprints, whose silence made the whole world stop and listen. By the time Oumuamua had vanished beyond the reach of our telescopes, a quiet curiosity had begun to ripple through the scientific community. Perhaps what we'd seen wasn't a one-of-a-kind visitor at all. Maybe the galaxy is full of travellers like it, faint, nearly invisible wanderers that move not because of engines or miracles, but because even solid rock can exhale when warmed by sunlight. The idea sounds poetic, almost fragile, a stone that breathes, but it comes from physics as gentle as it is powerful. Imagine a surface baked for millions of years by cosmic radiation, atoms rearranged, trapped hydrogen woven through the ice like tiny bubbles. When such a body drifts close to a star, the warmth seeps in. The trapped gas stirs and wriggles free, seeping outward in a slow whisper. The thrust is tiny, perhaps a feather's weight spread over a mountain, but in the emptiness of space, even that can change path. This is the dark comet hypothesis, shaped by researchers who studied the subtle deviations of small near-Earth asteroids. 6 of these familiar rocks, long assumed inert, were found to move ever so slightly off the courses predicted by gravity alone. They didn't shine, didn't trail mist, but the numbers betrayed a faint extra push, like someone gently tapping the scales when we weren't looking. What made the theory elegant was its humility. It didn't need alien sails or exotic substances. It simply required that our senses and our instruments might not see everything that happens when ice and radiation meet. Hydrogen, after all, is the lightest of gases. When released, it's invisible, odorless, and nearly impossible to trace at cosmic distances. To our telescopes, such outgassing would leave no visible mark, no halo, no glittering tail. But it could still nudge an object just enough to mimic a mystery. To visualize it, think of holding your hands near a block of ice on a sunny day. The air around it feels still, yet molecules are escaping constantly, each one too small to see but together enough to reshape the surface over time. In space, there's no breeze, no friction. The smallest release of gas acts like a jet engine that never stops. That picture of something solid but quietly breathing changed how astronomers looked at the familiar bodies orbiting near Earth. It meant that some asteroids might not be completely dry after all. They might carry, buried deep beneath their crusts, pockets of volatile materials, water ice, carbon dioxide, or molecular hydrogen, waiting for sunlight to wake them. The traditional line between asteroid and comet, between rock and ice, began to blur. Nature, as it turned out, doesn't file things into tidy drawers. If that's true, Oumuamua wasn't unique. It was simply the most dramatic member of a hidden population. Some researchers call them transition objects, though the term dark comets feels gentler, truer to their ghost-like nature. They are the quiet exhalers of the solar system, whispering gases too thin for our eyes to catch. Testing this idea isn't easy. The accelerations involved are almost unimaginably small. For a typical dark comet, the added speed might be only a few millimeters per second, less than the pace of a crawling insect. Yet over months and years, those millimeters accumulate into measurable differences. That's why precise tracking, not visual appearance, becomes the astronomer's art. It's like noticing that a clock's shadow moves just a fraction faster than the sun. A few future missions may soon help settle the debate. The Japanese spacecraft Hayabusa 2, famous for collecting samples from the asteroid Ryugu, is set to fly past another small world, 1998 KY26, around the year 2031. This asteroid spins incredibly fast, once every 10 minutes, and may share traits with the dark comet family. If Hayabusa 2 can measure even a hint of escaping gas or surface change, it could tell us whether such objects really do breathe invisibly. Meanwhile, Earth's largest new telescopes prepare to search the skies with more patience than ever before. The Vera Rubin Observatory in Chile will scan the entire visible sky every few nights, mapping motion after motion until patterns emerge. NASA's upcoming NEO Surveyor will look not in visible light but in infrared, the gentle warmth of objects that might be dark to the eye but still glow faintly in heat. Both instruments will be able to spot travellers like Oumuamua far earlier, giving scientists time to prepare an interception if one ever passes close again. ESA's Comet Interceptor mission, waiting patiently at a gravitational balance point, is designed for exactly that. It will sit in quiet readiness until a pristine comet, or perhaps even an interstellar visitor, appears, then race out to meet it. The hope is to study such a body before sunlight changes it, before its secrets evaporate. In a sense, it's a promise to the next messenger. We won't miss you this time, and so, while Oumuamua itself fades into the outer dark, it leaves behind an entire new field of study, a reminder that small things can alter the course of big ideas. The concept of dark comets reshapes how we think about the solar system, not as a place of tidy categories, but as a continuum where rock and ice, silence and motion are just points on the same spectrum. If you think about it, there's something almost comforting in that. The universe doesn't insist on sharp borders. It allows for grey areas, for in-betweens. Even here on Earth, we see it everywhere. Mountains that become mist, rivers that turn to cloud, boundaries that soften into belonging. Perhaps the cosmos itself moves by the same rhythm, blurring the edges of what we think we know. As night deepens, imagine these dark comets gliding silently across the void, their faint invisible breaths pushing them along paths that no one has drawn. They travel without spectacle, without trails of light, like ideas waiting centuries to be noticed. We may not yet know how many of them there are or what stories they carry, but each one reminds us that motion can exist even when nothing seems to move, and that sometimes the universe speaks in whispers too soft for us to hear until we learn how to listen. For centuries, astronomy has been a science of waiting. We cannot summon comets or move stars into position. We can only build our instruments, prepare our questions, and wait for the sky to offer an answer. That quiet patience now guides a new kind of ambition, the desire not just to observe the next mysterious visitor from afar, but to meet it. If Oumuamua taught us anything, it was that surprise comes without warning. By the time our telescopes found it, the object was already leaving. It had slipped past our sun like a stranger stepping through a doorway, gone before we even turned our heads. So scientists began to ask, what if, next time, we were ready? What if we could intercept the next interstellar visitor before it vanishes into darkness? The question may sound like science fiction, but plans for such a mission are already taking shape. The European Space Agency has a craft called Comet Interceptor, a patient spacecraft that will wait quietly in a place where gravity balances itself, a cosmic still point about 1.5 million kilometers from Earth. It will linger there, powered down but alert, like a fisherman waiting beside calm water. The idea is simple in spirit, complex in detail. The spacecraft will wait until telescopes spot a comet, or perhaps another interstellar object, on its way toward the sun. Then, with almost no time to spare, it will spring to life, adjust its path and rush out to meet the visitor before sunlight can reshape it. It will release smaller probes to circle and photograph, to measure the gases and dust, to touch the pristine material that has never felt warmth since the dawn of the solar system, to wait in stillness, ready for the unknown. That may be the most human form of curiosity there is. But Comet Interceptor isn't alone in this quiet vigil. Across the desert peaks of Chile, the Vera Rubin Observatory prepares for its first wide-sky scans. Unlike traditional telescopes that stare deeply at one point, Rubin will sweep the entire visible sky every few nights, recording its every change. Its digital eye will capture the flicker of supernova, the dance of near-Earth asteroids, and, perhaps, the faint trace of another Oumuamua drifting among the stars. To understand what makes Rubin special, imagine drawing a picture of the night sky once a week for 10 years. You'd begin to notice tiny differences, a dot that shifts slightly, another that brightens, one that seems to wobble. Over time, those small movements reveal orbits, distances, and stories. Rubin's telescope will do this automatically, building a living movie of the heavens, one frame every few nights. When a new object appears, the software will recognize its speed, compare it to known bodies, and alert astronomers around the world within hours. If Oumuamua had passed just a few years later, Rubin would have seen it much sooner, while there was still time to send a message to a waiting spacecraft like Comet Interceptor. Farther ahead, NASA's NEO Surveyor mission will join the watch, but it will look at the sky in warmth rather than light. Instead of visible images, it will capture the soft infrared glow of objects too dark to reflect much sunlight. A rock as black as charcoal might look invisible in ordinary light, but still emit a faint signature of heat. By measuring that warmth, astronomers can find asteroids and comets that optical telescopes would miss entirely. It's like trying to spot someone in a dark room. You might not see their face, but you can sense their presence by the heat in the air. Together, Rubin and NEO Surveyor will act as the eyes and the ears of this new era of celestial listening, one tuned to brightness, the other to warmth. And somewhere beyond Earth's orbit, Comet Interceptor will be the hand that reaches out when something interesting appears. There's another mission already on its way that may test these ideas in miniature. Japan's Hayabusa 2, which completed its main journey by visiting the asteroid Ryugu and returning samples to Earth, will continue on to a second rendezvous, an encounter with a tiny, fast-spinning object called 1998 KE-26, around the year 2031. This asteroid spins once every 10 minutes, so quickly that it bulges slightly at its middle, held together mostly by its own weak gravity. Scientists believe it may show traces of the same invisible forces suspected in Oumuamua and the dark comets. A faint breath of gases escaping through microscopic pores, too delicate for our eyes to catch. If Hayabusa 2's instruments detect even the subtlest trace of this phenomenon, it will help confirm that invisible outgassing really can change an orbit. When you hear phrases like infrared observations or non-gravitational acceleration, they can sound remote, mathematical. But beneath them lies something tenderly simple: light and warmth, motion and patience. We're learning in essence to see in more than one way, to recognise that the cosmos speaks not only in brightness but in temperature, not only in orbits but in hesitations and stray motions. The future of exploration will depend on that kind of awareness. Just as a sailor reads the colour of the sea and the texture of the wind, astronomers must learn to read the subtle hints of motion that whisper through their data. These spacecraft, the watchers and the waiters, are not tools of conquest. They are instruments of empathy, teaching us to listen for the softest signs of change. And there's something poetic about the idea that our most advanced machines are learning to wait, not rush. They sit in balance, at points where the pull of the sun and earth cancel each other, conserving energy, conserving attention. Waiting, like good listeners. Somewhere in that balance lies a kind of hope. The next Oumuamua will come, whether tomorrow or 1,000 years from now, and when it does, we may finally be ready, not to capture it, but to greet it properly, to ask gently what it has seen and what it carries from the stars. Perhaps, in that moment, the universe will answer not in language but in detail. A shift of light, a curve of gas, a memory etched into ice. The data will flow back to Earth like a long, slow exhale, and we'll listen, not to solve everything at once, but to feel, once again, that quiet joy that comes from understanding something new, however small. In the end, these interceptors aren't about chasing comets or hunting aliens. They're about learning to meet the unknown halfway, to build our patience into the machinery itself, to say to the cosmos softly, "We're here, and we're listening." If Oumuamua was a mystery that brushed past us from the farthest reaches of space, the next one drifted much closer. So close, in fact, that it hung above the ocean, shimmering on radar screens and in the memories of pilots who still struggle to explain what they saw. It happened in 2004 off the coast of California, when a group of US Navy aviators training from the aircraft carrier Nimitz encountered something they couldn't identify. They called it the Tic Tac because it looked exactly like one. Smooth, white, oblong, with no wings, no tail, no visible engine. What followed has become one of the most studied incidents in the modern history of unidentified aerial phenomena, what used to be called UFOs. Yet the way it unfolded, when told gently, feels less like a scene from a thriller and more like a strange dream. The day was calm. The radar operators aboard the ship had been tracking odd blips for nearly a week, small objects that appeared high above the ocean, moving erratically, then vanishing without pattern. Some climbed to heights of around 24 kilometers, then plunged down to the surface of the sea in less than a minute. Others hovered, motionless against the wind. When the pilots were sent to investigate, they saw something hovering just above a patch of disturbed water. It was bright white, about the size of a fighter jet, but perfectly smooth. No markings, no exhaust, no shadow of heat. As one pilot began to circle, the object seemed to notice, as though aware of being watched. Then, with a motion both graceful and shocking, it accelerated away. Within a heartbeat, it vanished from sight. Moments later, radar operators on the ship found it again, about 60 kilometers away. It had moved that distance in less than a minute, far faster than any known aircraft could safely travel. For many, this was a turning point. Here was a case with multiple observers, radar confirmation, and video footage captured by the aircraft's infrared targeting camera. The footage showed a small white shape darting across a grey background, tilting slightly and accelerating smoothly as if weightless. When the clip became public years later, it reignited global curiosity about whether something extraordinary might truly be sharing our skies. But scientists, as always, had to ask the quieter question: how reliable is the data? The more people examined the videos and radar logs, the more complex the story became. Modern military sensors are powerful but not infallible. They can be tricked by reflections, electronic interference, or atmospheric conditions. The human eye, too, is easily misled when distance and scale are uncertain. A small object close by can seem enormous if we assume it's far away. And the ocean, with its layers of heat and moisture, can bend radar signals in strange ways, creating phantom targets where none exist. The Nimitz incident became a study in perspective. How different instruments, each trustworthy on its own, can produce confusion when combined. The ship's radar saw one story, the pilot's eyes another, the infrared camera yet another. When stitched together, the puzzle looked surreal, but separate the layers, and much of it could be explained by a mix of sensor limits, weather, and expectation. None of this means that what the pilots saw wasn't real. It simply reminds us that reality, especially at high speed and high altitude, can be slippery. The sky is a noisy place, full of reflections, glints, and illusions. Even so, the Navy took the reports seriously. Instead of dismissing them, officials encouraged more pilots to document what they saw. In doing so, they quietly changed the culture of aviation. For decades, pilots feared that reporting strange sightings might harm their careers. Now they were told the opposite: report, observe, record, because every mystery is a potential clue about how the environment or our instruments behave. By 2022, the number of documented UAP reports had grown to over 500, many with data from multiple sensors. The US Department of Defense established an official office to review these cases, the All-Domain Anomaly Resolution Office, or AARO, and began releasing public summaries. Most of the objects, the report said, turned out to be ordinary balloons, drones, weather phenomena, or misidentified aircraft. But a small fraction, around 3%, remained unexplained due to lack of data. It's important to pause here, because the word unexplained doesn't mean alien, it simply means the evidence is incomplete. In science, mystery is not proof of the extraordinary. It's a signpost that more observation is needed. The mystery of UAPs is less about visitors from elsewhere, and more about how we perceive and measure a world filled with signals we don't yet fully understand. NASA entered the conversation in 2023, not to chase sources, but to apply open scientific standards to the issue. Their independent study recommended that data be gathered in a consistent, transparent way. metadata preserved, sensor types logged, and observations shared publicly whenever possible. In other words, to replace wonder mixed with fear by wonder guided by clarity. The same lesson echoes across all branches of exploration. Whether we're listening for whispers from deep space or puzzling over lights in our own atmosphere, the first step toward truth is to gather better notes. A mystery is like music heard through static. The clearer the recording, the easier it is to tell melody from noise. Sometimes people who report such sightings feel dismissed or laughed at, and that's unfortunate. Curiosity should never be punished. Most who report these things are not looking for fame. They're describing what they saw, often with genuine confusion. A good scientist listens first, then questions. The act of listening, carefully without mockery, is itself a form of respect for the unknown. The story of the Nimitz tic-tac and the growing number of UAP cases shows that curiosity is shifting from secrecy towards science. The aim is not to declare belief or disbelief, but to replace speculation with understanding, step by patient step. In the end, what makes these stories compelling isn't the hope of proof, but the reminder that even here, in our modern world of satellites and sensors, the sky still holds wonder. Some mysteries may one day shrink under the weight of data. Others may linger, resisting explanation, not because they defy science, but because science, at its best, moves with humility. Above the ocean, where radar waves meet the shimmer of heat, something still dances unseen. It might be wind, or water, or something we've yet to name, but even that uncertainty is precious. It keeps us looking up. The year after the public release of the Navy's Tic-Tac videos, something subtle but profound began to shift. The conversation around unidentified aerial phenomena, those puzzling specks of radar and light, moved from the realm of secrecy into the sunlight of science. For decades, such reports had lived in the shadows, surrounded by whispers, conspiracies, and the heavy weight of classified files. But science, like sunlight itself, works best when it shines evenly across everything, even uncertainty. In 2023, NASA convened an independent study team to examine the UAP issue, not to confirm wild stories, but to ask how we might approach them more carefully. Their conclusion was surprisingly gentle. The problem wasn't the mystery itself, but the lack of good data. Most sightings lack the kind of information scientists rely on: timestamps, sensor calibration, viewing angles, and environmental context. In a sense, we were trying to solve puzzles with missing corners. The team proposed something beautifully simple: make the unknowns open, collect reports using consistent methods, preserve the metadata, the digital fingerprints that tell us not only what was seen, but how and when it was recorded, share it publicly, so that independent scientists, engineers, and even curious citizens could help. Because mystery does not belong to governments. It belongs to everyone who looks up. In a world where so much information hides behind locked servers and classified documents, that suggestion felt almost revolutionary. Openness isn't always comfortable. It invites disagreement, even embarrassment. But it's how progress happens. The moment we can all look at the same sky with the same instruments, the wonder becomes shared, and so does the truth. NASA's report also emphasized humility. Even advanced sensors can be fooled. Many of the famous triangle-shaped lights seen in night vision footage turned out to be ordinary stars or aircraft, distorted by the camera's aperture, transformed into shimmering triangles by the geometry of the lens. Some fast-moving orbs were bright planets glimpsed through thin clouds. Others were drifting balloons catching sunlight near the horizon. Each explanation may seem mundane, but collectively they highlight something deeper: how the interface between technology and perception can create illusions that feel profound. Understanding this doesn't make the sky less magical. It makes it more so. Because every time we peel away an illusion, what remains is not disappointment, but refinement. We learn how to see better. The magic simply moves to a new layer, waiting to be found again. The new approach to UAP study borrows from astronomy's oldest lessons. Centuries ago, early observers mistook the fuzzy halos around stars for celestial clouds or angelic fires. Only later did better optics reveal them as artifacts of the telescope's glass. The lesson endures. Every discovery begins with the courage to admit what we might be misseeing. The same principle applies today. When scientists talk about data pipelines, a phrase that sounds cold and mechanical, they mean something very human. The path from raw observation to understanding. It's a journey full of delicate steps. Data must be collected, cleaned, and interpreted. Each step can distort the picture if handled carelessly, like a photograph printed with too much contrast. By making these pipelines open and transparent, NASA hopes that anyone, anywhere, can trace the story of a single observation from its first detection to its final explanation. In that transparency lies trust. A few countries have already begun to follow this model. France's National Space Agency maintains a public archive of aerial phenomena reports available to anyone online. In Chile and Canada, pilot reports are reviewed by both air safety and scientific organisations, ensuring that unusual sightings are examined with equal parts curiosity and caution. Slowly, the pattern is spreading. Instead of hiding the unknown, we study it together. This approach changes the tone entirely. Instead of believers and skeptics, we now have contributors. Instead of mockery, collaboration. It turns what was once an argument into a shared investigation, and perhaps that is what the subject always needed. Not a verdict, but a method. There's something deeply poetic about that shift. The sky has always belonged to everyone. Every child who has looked up at night has wondered if they were being watched in return. For centuries, that question carried fear or awe. Now, it carries a quiet invitation to observe more carefully. At the heart of all this lies a reminder about what science really is. It's not a pile of facts or a list of answers. It's a way of being honest with what we don't yet know. It asks for evidence, but also for patience. When handled gently, even uncertainty becomes a form of progress. The next generation of observatories will embody this spirit. The same telescopes searching for dark comets and distant planets will also scan for bright, fast-moving objects near Earth's atmosphere. Satellite constellations will map the air around us with unprecedented clarity, helping distinguish between weather, wildlife, and whatever still resists classification. Machine learning algorithms will sift through millions of hours of sky footage, not to prove or disprove alien life, but to understand how light, air, and instrument noise can dance together to make the sky seem alive. If something truly new is out there, this is how we'll find it. Not by chasing rumours, but by letting the evidence rise gently to the surface, like stars emerging as twilight fades. And maybe, just maybe, when we treat mystery not as a threat but as a teacher, it begins to respond in kind. The universe is not obligated to explain itself to us, yet it keeps offering clues. A shimmer on the radar, a fleeting shape in the clouds, a data point that doesn't quite fit. It's as if it's saying, here, look again, but this time, look closely. Open science is, at its heart, a promise. It tells us that truth isn't hidden behind walls or waiting in secret hangars. It's in the shared sky above us, in the willingness to record and compare, to admit mistakes, to learn publicly. It's in every person who chooses to look up with curiosity rather than fear. When you think about it that way, even the phrase unidentified aerial phenomenon becomes gentle, almost poetic. It means not something impossible, but simply something not yet known. And those are the most beautiful kinds of things there, are the ones that invite us to keep watching. So the next time you see a strange light drifting above the horizon, perhaps you won't rush to label it. perhaps you'll just take a quiet moment, breathe, and remember that every mystery, when met with openness, becomes part of the great conversation between us and the cosmos. If you step outside on a clear night and listen, you might almost hear it. The hum of distance, the soft static of space between stars. We send our signals out into that dark, carrying voices, music, the pulse of our technology. But all that human noise, everything that has ever left this planet at the speed of light, fills only a tiny sphere, a small, invisible bubble expanding at about 300,000 kilometers per second. After a century of broadcasting, that bubble is only about 60 light years wide. 60 years of light sounds vast, yet compared to the galaxy, it's barely a droplet in an ocean 100,000 light years across. Imagine standing at the edge of that ocean. The stars shimmer like reflections on moving water. Somewhere, perhaps, others are sending their own signals, each wrapped in their own expanding spheres of soundless radio waves. Some bubbles may already overlap, brushing like soap films. Others may never touch at all, separated by gulfs so immense that even light itself would need millennia to cross them. In that context, the famous question, "Where is everyone?" takes on a different tone. Maybe no one is missing. Maybe the party is simply spread across too large a hall, and the music hasn't reached us yet. This is the quiet heart of what physicists call the Fermi paradox, the tension between the vastness of space and the apparent silence within it. With hundreds of billions of stars, many hosting planets, it seems almost inevitable that life should have appeared elsewhere. And yet, from our small perch, we hear nothing that we can clearly recognize as intelligent. We are like travelers standing on a beach, listening for voices across a cosmic sea and hearing only the waves. One reason may be that we've only just begun to listen. For most of human history, we didn't have the tools to detect faint radio whispers from across the galaxy. Even now, our most sensitive instruments can only scan a fraction of the frequencies, directions, and time windows where a real signal might hide. It's as though we've dipped a single glass into the ocean and wondered why we didn't scoop up a whale. Astronomers often speak of two approaches to searching for cosmic companions. One is the wide sweep, listening to as much of the sky as possible, hoping to catch a brief but bright transmission. The other is the deep stare, focusing for long stretches on a single promising star system, waiting for a faint, steady pattern to rise out of the background. Each method has its strengths, and each risks missing something important. The wide sweep might overlook quiet civilizations. The deep stare might miss one-time flashes. Our efforts so far have mostly used the wide approach, quick scans of millions of stars, glancing touches rather than lingering conversations. The challenge isn't only sensitivity, it's patience. Signals could come in bursts, repeating only once every few days or years. They could be encoded in patterns we don't recognize, or transmitted in wavelengths we rarely monitor. Optical flashes, beams of microwave light, even bursts of neutrinos or gravitational waves. The universe gives us a wide canvas, but we've only painted on one corner. Still, our listening has grown more sophisticated. The early SETI experiments of the 1960s used single receivers sweeping slowly across the sky. Today, vast arrays of radio dishes can listen in multiple directions at once. They capture terabytes of data every hour, enough to fill entire libraries daily. Artificial intelligence systems sift through the noise, looking for tones that drift in frequency, the telltale sign of a transmitter on a rotating world. A genuine signal would show a gentle slide in pitch as the planet's spin carried it toward and then away from us. But that drift, that subtle shift, is measured not in rigid symbols or cold equations. It's more like a musical quality, a vibrato in the cosmos. To describe it, scientists use units called hertz per second. But you can think of it simply as how quickly a note glides from one tone to another. The universe, in this sense, is not silent. It's full of sliding, whispering notes, most of them natural, some perhaps not. And what about our own transmissions? They too drift outward, fading as they go. The first television signals, weak and uncoordinated, are now more than half a century light-years away, washing through clusters of nearby stars. If anyone is listening there, they might detect faint echoes of our early news broadcasts and radio dramas, flickering ghosts of laughter and music riding on waves of static. Beyond that distance, our noise blends into the background, indistinguishable from the hiss of the universe itself. Some scientists suggest that intelligent life may prefer not to shout at all. Broadcasting takes energy, and it can make a civilization visible to anyone who might wish it harm. Silence, in that sense, can be strategy, a cosmic form of privacy. Others imagine that advanced species might use technologies we don't yet know how to recognize. Laser bursts shorter than a blink, quantum-encoded messages, or something so subtle that it passes through us unnoticed. When you picture the galaxy this way, as a dark sea filled with scattered islands of awareness, it becomes less surprising that we haven't yet met our neighbours. The distances are enormous, the lifetimes of civilizations brief compared to the age of stars. Our radio bubble, still small and fragile, has barely touched the nearest ripples. We're the newcomers, the children at the edge of the playground calling into the wind, and yet there's something profoundly comforting about that image. It means we are part of a grand unfolding conversation that may last billions of years. Somewhere, perhaps, another world is building its first radio telescope tonight, sending out its first experimental signal, wondering if anyone is out there. Their bubble of sound will expand too, eventually brushing against ours. When that happens, it won't be a shock, it will be recognition. For now, we listen. We refine our instruments, learn to separate the chatter of satellites from the whisper of stars, and wait. The universe, patient as ever, waits with us. The silence isn't empty. It's simply full of space where understanding will one day bloom. And while we listen, our own transmissions, songs, greetings, and data keep moving outward, carrying the story of a small species that learned how to look up and to wonder aloud. In the stillness between those signals, perhaps that's all the universe needs to know about us for now. That we are here, that we're curious, and that we're still learning how to listen. Imagine you're sitting in a quiet cafe near a train station. Dozens of conversations murmur around you, voices rising, falling, crossing over one another. You catch fragments, laughter, a few words in a language you don't know, the shuffle of newspapers. Then, for a second, someone says your name from across the room, but you're stirring your coffee and the moment slips away. The voice fades and you never know who it was. That's what our search for life beyond Earth might be like. The universe could be speaking right now, not with words but with flashes, pulses, or patterns of light and radio waves. But we might be looking away, or listening in the wrong way, or not recognizing the call when it comes. When scientists talk about missing a signal, they don't mean negligence. They mean the sheer complexity of cosmic timing. Imagine that somewhere a civilization decides to transmit for a single day every century, using a narrow beam pointed toward our sun. If we happen to be looking elsewhere during that brief day, or if our instruments aren't tuned to the right frequency, we'll never know. Our galaxy rotates once every few 100 million years, its stars drifting in gentle spirals. That motion alone changes our line of sight constantly. In other words, the cosmic cafe is full, but every table keeps moving. The challenge of missing a hello became vividly clear in 1977, when a telescope in Ohio heard a burst of radio energy that lasted 72 seconds. A single note, about 30 times stronger than the background. It was so clean, so deliberate seeming, that the astronomer on duty circled it on the printout and wrote "wow" in the margin. It became one of the most famous exclamations in the history of science. The signal never repeated, The telescope's design, with its two large horns fixed side by side, meant that the source should have appeared in both. A few minutes apart if it were real, it appeared in only one. Later, researchers realised that the telescope's scanning pattern might have missed the repeat. The Earth's rotation had shifted the second horn just far enough away that the source, whatever it was, had already passed out of view. That single missed moment left us with a haunting question. Was it an echo of intelligence, or just a cosmic coincidence? Since then, the technology of listening has improved enormously. The Breakthrough Listen project, using some of the world's largest radio dishes, now scans millions of stars across billions of channels simultaneously. The data is so vast it can't be stored in traditional databases. It's streamed, sifted, and checked by algorithms that learn to recognize the signatures of interference from satellites, phones, and computers. Sometimes these algorithms find something that looks promising, like in 2019, when a signal appeared near the direction of Proxima Centauri, our closest stellar neighbour. It drifted slowly in frequency, just as a transmitter on a rotating planet would. It lasted several hours. Then, when the team looked closer, they found the same pattern appearing in other data, on frequencies used by electronics inside the telescope's own computers. It wasn't a message, it was our own reflection. That realization didn't bring disappointment, it brought relief, because it proved the system worked. The search was honest enough to debunk itself. Science grows stronger not when it finds miracles, but when it refuses to keep them untested. The real wonder isn't in the false alarm, it's in the process that turns mystery into understanding. The universe, however, still has ways of surprising us. Not all signals are artificial, but not all are ordinary either. In the last decade, astronomers have detected thousands of brief, brilliant flashes known as fast radio bursts. Bursts so short they last only a few thousandths of a second, but so powerful they can outshine entire galaxies during that heartbeat of time. Some repeat, most do not. A few have been traced to magnetars, neutron stars with magnetic fields so intense they could erase a credit card from halfway to the moon. When their magnetic crusts crack, they release titanic energy that ripples across space as a quick, sharp ring. These flashes are natural, but they teach us humility. A century ago, we wouldn't have believed such phenomena possible. Today, we know the cosmos has more ways to make light sing than we ever imagined. So when we search for voices beyond Earth, we must remember that nature too is a brilliant musician, capable of improvising every note we thought belonged only to intelligence. Modern observatories like the Keim telescope in Canada now detect several of these bursts every day. The data fills with them, thousands per year, all arriving from different corners of the sky. Some last less than a blink, others stretch to the length of a human breath. None have carried a message yet, but each reminds us how narrow our expectations once were. When we first listened, we expected steady tones, mathematical codes, perhaps even greetings. Instead, the cosmos answered with thunderclaps. This doesn't mean the dream of hearing another civilization is over. It means we're learning how to recognize patterns we once would have missed. A true techno-signature, the trace of technology itself, would have to stand apart from the wild orchestra of natural signals. It would need to be narrow, precise, repeating in a way that speaks of intent. That's why scientists now run simulations, injecting artificial test signals into real data streams to make sure their systems can still catch them. It's like practicing for a symphony you've never heard, but hope to recognize instantly when it starts. Some groups are even thinking beyond radio. What if the messages are written in light, using flashes of lasers aimed across interstellar distances, or encoded in the positions of pulsars, those spinning remnants of exploded stars whose beams sweep the cosmos with clock-like regularity? Perhaps the signatures are hidden not in time, but in structure, in how molecules or magnetic fields arrange themselves. Each possibility expands our sense of what communication can be. It's easy to imagine frustration when years pass without a clear hello. But most scientists describe the feeling differently. They talk about serenity, about knowing that every quiet night spent listening is part of something grander. Each null result isn't failure. It's a boundary drawn on the map of what's possible. It tells us where the silence truly lies, and therefore where to listen next. The truth may be that the galaxy is alive with communication, and we simply lack the ears to hear it. But as our technology evolves, our hearing sharpens. Projects like Cosmic, an experiment that listens for alien signals while simultaneously observing cosmic phenomena, are making this kind of dual listening the norm. Every observation becomes two things at once: a look at the natural universe and a question whispered toward intelligence. So when we ask why we haven't heard from anyone yet, maybe the answer isn't that we're alone. Maybe it's that we've just arrived too early to the concert. The instruments are tuning, the notes still faint. One day, a melody might rise above the hum, a simple pattern, a rhythm that repeats, a hello wrapped in mathematics or music. And when it comes, we'll understand, not because it sounds alien, but because it sounds deliberate. Until then, we listen carefully, knowing that silence itself is a kind of message. It tells us that the universe is patient, that discovery happens on its schedule, not ours. And when the next whisper comes, we'll be ready, not to claim ownership of it, but to answer softly, "We hear you." On a warm August night in 1977, a radio telescope near Columbus, Ohio, sat quietly listening to the sky. It was called the Big Ear, a name that suited its purpose perfectly. Its two giant rectangular horns looked like shallow valleys of aluminum, each patiently catching the faint rain of radio waves that fall constantly from space. Inside, computers printed long ribbons of numbers and symbols, the steady heartbeat of the cosmos turned into code. Most nights it was nothing but background noise, a whisper of static left over from creation itself. Then, just after 10 p.m. on August 15th, a single tone burst from that quiet sea of randomness. For 72 seconds, about the time it takes to tie your shoes or make a cup of tea, the telescope heard a signal far stronger and purer than anything in memory. It came at a special frequency, a gentle hum near 1,420 million cycles per second. The natural tone emitted by the simplest atom in the universe, hydrogen. Because hydrogen fills the cosmos, astronomers had long thought that any species trying to say hello might choose that same pitch, the universal dial that every civilization would know. The signal rose, peaked, and fell exactly as expected for something drifting through the telescope's field of view as the Earth turned. It wasn't a blip of equipment noise, nor the stutter of a satellite. It had the graceful shape of something real. When astronomer Jerry Eman reviewed the paper printout later, he circled the long string of numbers that marked the moment, 60Q, and, almost involuntarily, wrote one word in the margin: "Wow." That exclamation has echoed for nearly half a century. It's one of the shortest scientific papers ever written. A single word that captured equal parts amazement and restraint. The "ow" signal, as it came to be known, remains one of the most tantalizing mysteries in astronomy. A perfect hello that spoke only once. The Big Ear's design was both brilliant and limiting. Its two listening horns sat side by side, separated by about 2 minutes of Earth's rotation. Any genuine signal from space would first appear in one, then, 2 minutes later, in the other. The wow appeared in only one. That meant either it vanished just after being heard, or it had slipped out of range before the second horn could listen. The telescope, fixed in place, couldn't turn to chase it. And so, when the moment passed, it was gone. Over the years, many tried to find it again. Dozens of follow-up observations returned to the same patch of sky, near the constellation Sagittarius, pointing toward the heart of our galaxy. Nothing. The space was silent, as though whatever had shouted once had fallen asleep forever. Scientists proposed explanations, each elegant in its own way. Maybe it was a reflection from a distant satellite, or a military transmission bouncing off debris. Some wondered if it could have been a rare outburst from a natural source, a comet releasing hydrogen gas as it passed through sunlight, briefly brightening the cosmic channel. In 2017, one team traced the possible path of 2 such comets that happened to cross that region of the sky around the right time. Perhaps they suggested the signal had been our own sun's light reflected in hydrogen clouds around those icy travellers. Yet others noted that the timing didn't fit perfectly, and no one has ever been able to recreate the effect. The truth remains a kind of cosmic shrug, a note without an author. To understand why 72 seconds matters, think of how the Big Ear listened. Each horn scanned the sky as the Earth's rotation slowly turned it beneath the stars. The telescope couldn't dwell. It caught each patch of sky for exactly the time it took for a star to drift through its field. Those 72 seconds. That's what astronomers call the integration time, the period during which light or radio waves gather in the instrument before fading into the next slice of heaven. If the wow signal had lasted any longer, it might have been picked up by the second horn as well, giving proof that it came from beyond Earth. If it had been shorter, we might have missed it entirely. It lived precisely in the narrow window that made it unforgettable and unrepeatable. There's a kind of poetic symmetry in that. The universe sometimes speaks to us in intervals too brief for certainty, as though testing whether we can live with not knowing. For decades, the wow signal has inspired both rigorous science and gentle wonder. Artists have painted its waveform. Musicians have turned its numbers into melodies. For some, it represents hope. The idea that maybe, once, we truly heard another intelligence. For others, it's a lesson in patience. Proof that discovery requires not only technology, but persistence measured in lifetimes. If you were to translate those 72 seconds into sound you could hear, it would be a simple rising tone, a soft note swelling, holding, and fading. Nothing dramatic, just a calm hum that grows out of the static like a sigh. In that sense, the wow was never a shout at all. It was a whisper, perfectly timed, that brushed past our attention long enough for one person to notice. We often think of science as a hunt for answers, but sometimes its beauty lies in the questions that stay open. The wow signal remains one of those open doors, not because it hints at aliens, but because it reminds us that the cosmos is capable of surprise. It tells us that even with all our instruments and algorithms, there are still moments that make us simply stop and say, "Look at that." Whenever astronomers aim their new telescopes toward the stars, they keep that printout in mind, the circled numbers, the handwritten wow. It's a quiet talisman of curiosity. Each new survey, from the massive arrays of dishes in Australia to the radio, telescopes buried in the deserts of California, carries within it the same hope, that one day another tone might drift through the static, steady enough to measure, gentle enough to understand. Maybe when it comes again, we'll have learned how to listen longer, how to follow it before it fades. Maybe we'll be able to point a second instrument in time to confirm that it isn't a comet or interference or a trick of rotation. Until then, the wow signal remains exactly what it was, a 72-second hum at the favourite frequency of hydrogen, the atom that built the stars, the oceans, and us. A simple hello written in the alphabet of the universe's most common element. And perhaps that's the most fitting. Beginning to any conversation between worlds, a note carried on hydrogen, soft, fleeting, but unmistakably real. Decades after the wow signal faded into the quiet, another whisper caught the world's attention. It arrived not from the 1970s age of punch-card computers, but from the high-speed era of digital radio astronomy. The year was 2019, and a team of scientists working with the Breakthrough Listen project, the largest coordinated search for extraterrestrial intelligence ever attempted, was combing through a sea of data from the Parkes telescope in Australia. In that flood of numbers, They found something. A narrow, steady tone that drifted slowly in frequency, just as one might expect from a transmitter sitting on a rotating planet around another star. It seemed to come from the direction of Proxima Centauri, the closest star to our own sun, only a little more than 4 light-years away, a cosmic neighbour. The signal was subtle but persistent. It lasted several hours, clean and unwavering, and for a moment it felt like déjà vu, the same breathless curiosity that had once surrounded the WOW event, half a century earlier. They called it BLC-1, short for Breakthrough Listen Candidate 1, the first plausible maybe of the modern search. It wasn't a burst or a spike, it was a single, thin thread of radio energy, holding its pitch like a note on a flute. To the team's instruments, it looked almost perfect, narrow in bandwidth, sliding gently over time as if it came from a spinning world and absent from other directions in the sky. What made it so compelling was its restraint. Real alien signals, if they exist, would likely look just like this: simple, intentional, patient. No voice, no melody, just the unmistakable mark of technology shaped by precision. And yet the astronomers knew better than to rush. The universe is a master of imitation. So they began the long process of verification, what one researcher called an autopsy of a beautiful maybe. First, they checked for interference. Modern telescopes are surrounded by human-made noise, cell towers, satellites, even the electronics inside their own systems. The Parkes telescope, like any observatory, lives in a constant blizzard of chatter from Earth. Sorting through it requires both machine learning and old-fashioned detective work. They re-examined the raw data, this time splitting it into many smaller pieces to look for patterns that might betray an earthly origin. Slowly the truth revealed itself, not as a single mistake, but as a coincidence of many small ones. The signal appeared to come from the sky, but it also showed up faintly when the telescope looked away, hiding among the background hum of the equipment. It wasn't always identical, but its rhythm and structure matched internal electronics rather than anything celestial. Somewhere deep in the maze of receivers and amplifiers, a tiny oscillation in the hardware had created a tone that just happened to mimic the pattern of a drifting extraterrestrial signal. It was as if the telescope had whispered to itself and overheard its own echo. For outsiders, the result might have been disappointing. For scientists, it was a quiet triumph. Because what mattered most wasn't that BLC-1 failed, but that the process worked. Every layer of testing, cross-checking, re-observing, comparing with control fields, functioned exactly as it should. Science, after all, is less about finding miracles than about learning how to tell the difference between miracle and mirage. In the days that followed, the team wrote up their analysis, openly publishing the full details of how the signal was found and then unmade. It became a case study in modern verification, a guidebook for how to be sure next time when the next whisper arrives. They describe their methods in gentle, human language: signal folding, drift correction, interference rejection. But behind every term lay something deeply poetic: the act of listening to noise until meaning emerges, and then having the honesty to admit when the meaning was ours all along. In a way, BLC-1 mirrored the nature of curiosity itself, the first thrill of discovery, the quiet excitement, the careful skepticism, the inevitable unravelling, and finally the peace that comes with clarity. It's the same rhythm that governs so many of life's pursuits, the cycle of hope and understanding. There's a certain grace in false alarms. They remind us that the universe is not obligated to make itself simple. They teach us to refine our senses, to build better tools, to trust process over passion. BLC-1 wasn't proof of alien life. It was proof that humanity can search carefully, without superstition, with wonder intact and reason in hand. And yet some researchers admitted to feeling a momentary ache when the verdict came in. That heartbeat of what if had stirred something deeply human, the longing to know that we are not alone, that somewhere across the dark another mind is awake and listening back. When that possibility dimmed, it felt like the lights in a distant window going out. But even that, they realised, was worth feeling. It meant we still care enough to wonder. The lessons from BLC-1 now ripple outward into every search project. Algorithms are being redesigned to recognise their own electronic ghosts. Receivers are shielded better, calibration runs more frequent. It's like tuning a piano after hearing a single wrong note. Each small correction brings the next song closer to harmony. If a real signal ever comes, it will survive this scrutiny. It will persist when every test says not noise. It will repeat, drift predictably, and remain visible no matter which telescope looks. When that day comes, we'll be ready. Because of false alarms like BLC-1, we'll know what not to believe, and therefore what finally to trust. In a universe that often hides meaning beneath layers of static, such patience is everything. The scientists behind BLC-1 didn't chase glory or headlines. They did something quieter and braver. They showed that wonder can coexist with discipline. They taught us that hope doesn't have to end when an illusion fades. It simply becomes sharper, more refined. So when people ask, was BLC-1 the one? The best answer is, not this time, but maybe next. Every no brings us closer to a yes worth believing. Each false tone teaches us to recognize the real symphony when it begins. And if you listen closely enough, there's beauty even in that silence, the kind that tells you the universe hasn't stopped talking. It's only paused, waiting for us to finish tuning our instruments. The story of cosmic listening didn't end with BLC-1. Long before that careful investigation in Australia, there was another case, one that began in the early 2000s, when data from a small project called SETI Home rippled through millions of home computers around the world. It was one of the first experiments to harness ordinary people's idle machines to search for something extraordinary, signs of intelligence hiding in radio noise. Each participant donated a sliver of their computer's power, downloading small chunks of telescope data, recorded by the Arecibo Observatory in Puerto Rico, the great radio dish that once listened to the stars through the jungle. When those computers finished analysing their assigned pieces, they sent the results back to Berkeley, where the software assembled them into a vast portrait of cosmic sound. One day, the network found something that stood out, a signal catalogued as SHG B02+114A, buried deep among billions of samples. The name, long and cryptic, came from its coordinates in the sky, a shorthand for the region near right ascension 2 hours and 14 minutes. But to those who worked with the data, it was more than a number. It was a note that seemed, at first glance, to have rhythm and intention. The signal appeared several times in roughly the same patch of sky, at a frequency near the favourite tone of hydrogen, the same cosmic wavelength that had carried the wow signal decades before. It drifted in pitch, sliding, gradually upward or downward, as though coming from a source that was rotating or orbiting. To some, it looked like the perfect candidate, not random, not persistent across all directions, but intriguing enough to make you wonder. For a few months, the astronomy community hummed with quiet excitement. Articles appeared in small journals and on early science forums. Could this be it? Could the old Arecibo dish have caught the next wow? This time with data precise enough to track. But as the analysis deepened, something odd appeared. The drift in frequency was too steep, as if the signal were coming from something spinning impossibly fast or moving in a way that defied the known laws of motion. To produce such a rate of change, an alien transmitter would have had to sit on a world rotating dozens of times faster than Earth, or orbiting its star at a speed that would rip it apart. The numbers simply didn't make sense for any stable planet. Then there was another problem. Every time the signal was detected, it began exactly at the same starting pitch, around that familiar hydrogen tone. That kind of precision, repeated over and over, wasn't something nature usually provides, and it wasn't what we'd expect from a faraway civilization either. Real radio transmitters, especially those on rotating worlds, would shift slightly each time. This one didn't budge. It was as if the sound had been painted on, not sung. Gradually, the excitement softened into understanding. The signal, almost certainly, was born not among the stars but in our own equipment, a product of the way the receiver processed and digitized data. The telescope hadn't heard an alien. It had overheard itself again, repeating a note of its own design. For many volunteers, this revelation could have been disheartening, but most of them didn't see it that way. They understood that participation itself was the adventure. Millions of people had, for a time, joined in a collective act of cosmic listening, and even if SHG BU2 2014A was an illusion, it proved that a network of ordinary citizens could process astronomical amounts of information, accelerating the pace of discovery. In truth, there was never just one signal to chase. Around the same time, a new class of cosmic sounds began to capture astronomers' attention. Real, but far stranger than anyone had expected. They were brief, intense flashes of radio energy lasting only a few thousandths of a second, yet powerful enough to outshine entire galaxies during their tiny heartbeat of existence. These were the fast radio bursts, FRBs. When the first of them appeared, some wondered if they might be artificial. After all, their brevity and precision seemed almost deliberate. But as more were found, patterns emerged. Some repeated, others did not. Some came from nearby galaxies, others from billions of light years away. The variety was breathtaking. Eventually, one was traced to a magnetaire, a type of neutron star whose magnetic field is so strong that it could erase the information on every hard drive on Earth if you could somehow bring it within a few thousand kilometers. When its crust shifted and cracked, the energy released into space as a brilliant radio pop, like a single note struck on a cosmic piano. What had looked like messages turned out to be natural events, yet not ordinary ones. They were the universe's own improvisations, fast and fierce. The cosmos wasn't quiet after all. It was singing in bursts, its own version of lightning in the dark. The connection between these bursts and ball lightning on Earth feels poetic, even if they share no physical link. Both are rare flashes of structured energy, one across galaxies, one across skies. Both remind us that nature's creativity often outpaces our imagination. And so, SSG2 plus E14A joined the gallery of almosts, signals that taught more through their unravelling than their discovery. Each one refined our listening, sharpened our skepticism, and strengthened our sense of wonder. Science, at its best, doesn't fear being wrong. It treats mistakes as the scaffolding for truth. Somewhere in all that static, amid the choir of natural and artificial tones, we continue to listen. Each algorithm is more sensitive, each telescope a little wiser. The false alarms are fewer now, but each one still carries its own small beauty, a reminder that even errors can hum with meaning when heard the right way. So if one day the real signal arrives, steady, repeating, undeniably crafted, it will not be because we were lucky. It'll be because we learned to hear carefully enough to tell the difference between our own echoes and another mind's hello. For now, the sky keeps singing in lightning bursts. Every few seconds, somewhere out there, a pulse crosses the void, lasting only a fraction of a heartbeat, carrying with it the power of a billion suns. It is not a voice, but it is music nonetheless. And when you lie in bed tonight, listening to the faint hum of your room, know that a similar hum is moving across space right now. An endless, bright whisper reminding us that silence too can be alive. Before we chase the next mystery far into space, it's worth pausing here, beneath our own sky, where the air hums and flickers during a thunderstorm, because not all enigmas live among the stars. Some drift through our atmosphere, glowing for a moment like fireflies of pure energy. They're known as ball lightning, and though people have described them for centuries, science still holds them gently, as if afraid they'll vanish if we stare too hard. The first accounts go back hundreds of years. Sailors spoke of orbs of light that rolled along their ship's masts, moving as calmly as lanterns carried by invisible hands. Farmers told of glowing spheres floating across fields, sometimes the size of a fist, sometimes as large as a melon. A few claimed the lights passed through walls or hovered above beds, silent but aware. Most of these tales sound like folklore, until you notice how consistent they are. Even across continents and centuries, something real was happening. In 1753, a Russian scientist named Georg Richman tried to measure the electricity in a thunderstorm using a metal rod, much like Benjamin Franklin had done in Philadelphia. When lightning struck the rod, a glowing sphere leapt from it and struck him in the head, killing him instantly. It was one of the first documented fatalities from what might have been ball lightning. Even in tragedy, the phenomenon announced itself in its own strange language of light. 2 centuries later, in 1963, a British pilot named R.C. Jennison was flying through a storm when a ball of light appeared in the cabin of his jet. It was about 20 centimetres wide, roughly the size of a small plate, and glowed with a soft white radiance. It drifted down the aisle in silence, passed through a bulkhead, and disappeared. The report was published in Nature magazine, not as rumour, but as an observation. Here was a man of science admitting he'd seen something the textbooks could not explain. For decades, no one managed to record the phenomenon on film. Then, in 2012, a team of physicists in China studying a thunderstorm accidentally captured it with a high-speed camera. The video showed a bright sphere descending from a lightning strike and gliding sideways for about a second before vanishing. More important than the footage itself was the spectrum, the fingerprint of its light. When they analysed it, they found distinct colours associated with elements like silicon, calcium and iron. That simple list, silicon, calcium, iron, offered the first tangible clue. The ground in that region contained all three, and when lightning struck the soil, it may have vaporized grains of sand and metal, creating a cloud of glowing nanoparticles. These tiny fragments could then burn and recombine, releasing energy slowly enough to appear as a stable orb. In other words, the lantern in the storm might not be made of plasma alone, but of matter briefly reborn in fire. Strange to think of soil becoming light. Yet that's what the evidence suggested. A momentary transformation of the solid world into something ethereal, carried by the breath of an electrical storm. You could call it alchemy, except the recipe involves nothing mystical, just the raw chemistry of heat and air. Still, the mystery refused to stay solved. Some reports described balls that lasted far longer than vaporized dust could survive. Others mentioned orbs passing unharmed through glass or wood. Behaviour that seemed to defy physics. Witnesses spoke of smells like ozone or sulphur, and faint hissing sounds as if the air were boiling. No single theory could explain all of it. Scientists began to suspect that ball lightning might not be one phenomenon, but several, different processes that happened to look alike. Some could be electrical discharges in thin air. Others might be reflections of distant lightning distorted by the eye. And perhaps a few are psychological, produced by the brain itself under the stress of storm and glare. The challenge was not that ball lightning didn't exist, but that it might exist in too many forms at once. What makes the subject captivating, even now, is how it sits at the border between folklore and laboratory science. Everyone knows what lightning is, yet this gentler cousin still evades capture. It has been described by ship captains, mountaineers, physicists and children, each using the same quiet awe. It floated, they say. It glowed. It felt alive. The mystery also reminds us that nature often hides its deeper truths inside rare events. Thunderstorms produce billions of ordinary lightning bolts every year, but perhaps only a handful of these luminous spheres. To witness one is to glimpse the exception. the universe testing out a different rule, if only for a moment. Imagine standing on a hill as a storm rolls in. The sky darkens, air thick with the scent of rain and static. A flash lights up the horizon, and for a heartbeat you see it. A glowing orb drifting just above the ground, moving with the wind but not quite obeying it. You don't hear thunder yet, only the soft hiss of rain on leaves. The sphere brightens, then fades, leaving nothing behind but the memory of its glow. Was it electricity, vaporized dust, or something stranger? You'll never know for sure, but you'll remember the feeling of seeing something both earthly and alien at once. That feeling, part fear, part wonder, is the heart of science. We chase it not to erase the mystery, but to understand it well enough to honour it. Every new observation brings us closer, and yet the phenomenon keeps slipping away, like a dream that vanishes when we try to retell it. When the Chinese video appeared, showing the faint fingerprints of silicon, calcium and iron, the scientific community quietly celebrated. Not because it solved everything, but because it gave us a bridge between folklore and fact. We could finally say, look, here is proof that something happened. That bridge matters. It connects imagination to evidence, myth to measurement, and standing on it, we can appreciate both sides, the story and the science. Somewhere tonight, as clouds build and winds whisper, another of those lanterns might appear. Maybe a camera will catch it this time, or maybe not. Perhaps it will glide past unnoticed, a brief bubble of the Earth's own light, reminding us that even in the places we think we know best, in our air, our storms, our own backyards, there are still pockets of magic left. It may not last more than a few seconds, but those seconds will be enough to remind us that the line between wonder and knowledge is not a wall, it's a shimmer, flickering like a lantern in the storm. For centuries, people could only watch ball lightning in awe, catching it by accident, never twice in the same place. But in the modern age, scientists began to wonder if they could summon it, if this glowing, ghostly thing could be invited into the lab instead of waiting for a storm to deliver it. It was a delicate ambition, like trying to bottle a rainbow or train a breeze, yet curiosity can make even impossible ideas worth trying. The first attempts were simple. Recreate a lightning strike, then see what happens next. At research centres from Moscow to Tel Aviv, engineers set up chambers filled with air and water vapour. They used high-voltage discharges, bursts of current hot enough to turn water into steam and dust into vapour. To their surprise, small glowing orbs sometimes appeared in the wake of those artificial strikes. They hovered for a few seconds, tiny, luminous clouds, almost like soap bubbles made of light. One experiment at the Max Planck Institute involved firing an electric pulse into a thin layer of water. The sudden burst of energy split the molecules into hydrogen and oxygen, creating a flash of plasma, a hot, glowing gas, and tiny droplets of silicon oxide, the same material found in sand. As the droplets cooled, they combined into nanoparticles, each just a few millionths of a millimeter across. When these particles met the oxygen in the air, they burned slowly, releasing light and heat. The result was a small sphere about the size of a marble, drifting above the dish for several seconds before fading away. In another lab in Tel Aviv, scientists tried something even more curious. They placed a sample of silicon inside a microwave oven, the same kind of energy that warms leftovers in your kitchen, and let the focused waves interact with the material. A glowing orb appeared above the sample, sustained by the constant bath of microwaves. It swirled and pulsed, forming a tiny sun inside the metal chamber. When they switched off the power, the sphere lasted a few moments longer, then vanished in silence. These experiments suggested that ball lightning might form when extreme energy rearranges ordinary matter into a temporary glowing state. It's as if the storm, or in this case, the laboratory, creates a new kind of cloud, one made of dust and electricity instead of water and vapor. The idea is elegant, that light itself can hold a shape, like a soap bubble balancing on air. But the search didn't end with glowing droplets. Some physicists began exploring the magnetic side of the mystery. They proposed that the orbs might be made not of burning particles at all, but of fields, tangled knots of magnetism and plasma that feed off their own structure. Imagine a ball of yarn, but each thread is made of invisible magnetic lines looping and crossing, trapping heat and charge inside. These loops could, in theory, hold together for seconds or even minutes before unravelling. To describe such self-contained knots, theorists borrowed a term from geometry and particle physics, skyrmions. The word sounds abstract, but the idea can be pictured simply as a knot that keeps its shape no matter how you twist it. A 3D skyrmion is like a knot tied into light itself, a whirlpool of magnetic energy wrapped around air. When researchers simulated these structures on computers, they found that they could behave like miniature ball lightning, stable, spherical, and surprisingly graceful. What makes this so fascinating is that these shapes echo patterns we see across nature. Tornadoes, whirlpools, and even galaxies form spirals that hold energy in balance. Ball lightning might be the smallest expression of that same cosmic principle: rotation creating order, balance creating beauty. And yet, the deeper scientists probe, the more they realize that no single explanation fits every story. Some balls behave like plasma, some like burning dust, others like organized magnetic fields. Nature seems to use more than one recipe to make its rarest lights. Perhaps ball lightning is not one phenomenon, but a family of phenomena, siblings rather than clones, each born from a slightly different dance of energy. In this way, the study of ball lightning becomes a mirror for science itself. We begin with awe, try to reproduce what we've seen, and then discover that what we thought was singular is many. The mystery multiplies even as understanding grows. But this multiplication is not failure, it's richness. It means that reality has layers, and that every time we lift one, another waits beneath it, shining faintly in the dark. Even if we can now create small glowing spheres in laboratories, we still haven't captured the full experience that witnesses describe. The eerie calm, the sensation of intelligence, the way the orbs move as though curious. Maybe that's because the laboratory is too controlled, too clean. The atmosphere of a thunderstorm, the turbulence, the moisture, the charge, may be an essential ingredient, impossible to duplicate exactly indoors. The true ball lightning might be not just a physical event, but an environmental one, a product of place and moment that can't be repeated on command. Still, each successful experiment brings us closer. Every glowing sphere on a lab bench is like a letter from nature, hinting at what's possible. They teach us that light isn't just something that shines, it's something that can live briefly, sculpted by forces we barely understand. The image of fire from water may sound contradictory, but it captures the paradox beautifully. From the calmest of substances, when struck by the fiercest of energies, comes a creation both delicate and fierce. It drifts quietly, consuming itself in brightness until it dissolves into air. And maybe that's what makes ball lightning feel almost spiritual to those who see it. It's a reminder that transience can be profound, that beauty doesn't need to last to be real, like a dream remembered only as light behind. Closed eyes, its impermanence is part of its grace. As you imagine these experiments, the spark flashing into mist, the small sphere hovering above a dish, think of how ordinary it all begins. Just air, water, silicon, electricity. The same ingredients that surround you right now. The difference lies only in energy and timing, in the choreography of chance. The universe, it seems, can weave magic from the simplest materials when the rhythm is just right. Perhaps that's why these orbs haunt us still. They're nature's way of showing that mystery doesn't always require distance. Sometimes it fits in the palm of a hand. glowing softly for a heartbeat before returning to the quiet that made it. Far beyond the orbits of the known planets, past the cold paths of Neptune and the silent haze of Pluto, there lies a region of dim, icy fragments that circle the sun like the leftovers of creation. It's called the Kuiper Belt, and for years it seemed quiet, just a frozen archive of ancient debris. Then, in the early 2010s, astronomers noticed something odd. A handful of these distant objects didn't behave as they should. Their orbits, long stretched ovals tilted at peculiar angles, seemed to cluster together as if pulled by the invisible gravity of something massive lurking in the dark. The discovery came quietly, one data point at a time. A telescope in Chile would spot a faint, slow-moving dot against the background stars. A survey in Hawaii would notice another, following a similar path. When researchers plotted these orbits together, a pattern appeared, subtle but persistent. The chances of such alignment happening by coincidence were tiny. The objects seemed to be dancing to a hidden rhythm. Something unseen was conducting the music. In 2016, two scientists, Konstantin Batygin and Mike Brown, proposed an audacious explanation. There might be a ninth planet, larger than Earth, colder than any known world, circling the Sun on an orbit so vast it would take 10,000 years to complete a single lap. They estimated it could be about 5 times heavier than Earth and orbit 20 times farther out than Neptune. In numbers, that means it could be well beyond 400 times the distance between the Earth and the Sun, a realm where sunlight is so faint that noon would feel like deep twilight. But we can't just leave those numbers floating in abstraction. To imagine this planet, picture a lonely marble glinting in a black ocean, tracing a path so wide that it spends most of its existence beyond our reach. If you placed it in our solar system's scale model, where Earth is the size of a pea, Planet 9 would be a small plum more than a kilometre away, circling in silence. The idea reignited the old thrill of discovery that once surrounded Neptune, which was itself predicted by mathematics before it was seen through a telescope. In the mid-1800s, astronomers noticed tiny discrepancies in Uranus's orbit and deduced that another planet must be tugging on it. When they pointed their telescopes to the predicted spot, there it was, proof that gravity, even when invisible, leaves a trace. Planet 9, if it exists, would be the next echo of that story. Its gravitational fingerprint appears in the odd clustering of smaller objects. Their closest points to the Sun, called perihelia, all lie in roughly the same direction. Their orbital planes tilt the same way. It's as though an unseen companion is shepherding them, pulling their paths into harmony. But not everyone agrees. Other surveys, particularly the OSIRIS project in Canada and the Dark Energy Survey in Chile, found that their data didn't show the same pattern. They argued that the clustering could be a mirage created by where and how we've looked. If you only search certain parts of the sky, you'll find coincidences that vanish when viewed in full. It's the celestial version of walking through a city at night and concluding that everyone leaves their lights on, simply because you're only passing the houses where windows glow. To test whether the pattern is real, astronomers need more objects, more icy crumbs from the edge of the solar system to map the invisible curve of gravity. But spotting these faint wanderers isn't easy. They're smaller than mountains, darker than charcoal, and so far away that even reflected sunlight reaches us as a trickle. The biggest telescopes can barely tease them out of the background stars. Tracking their movement requires patience measured in years, yet the allure of the hunt is irresistible. Because if Planet 9 does exist, it would be the most distant world ever discovered in our system. A planet that has never known warmth, where the sun is no brighter than a coin seen from 100 meters away. Its atmosphere, if it has one, might be frozen nitrogen and methane, forming wisps of frost that drift like smoke. Its surface could be smooth as glass, scarred only by the slow fall of ancient comets. Some models even suggest it might be a failed ice giant, A world like Neptune that was flung outward during the early chaos of solar formation. Perhaps it has spent billions of years in exile, orbiting in solitude, carrying within it the chemistry of a time when everything was still colliding and forming. The thought that such a world could exist just beyond our detection feels both humbling and comforting. It reminds us that our solar system isn't a completed puzzle, it's a work still in progress. There may still be pieces scattered under the cosmic table waiting to be found. If the clustering of orbits is indeed real, then gravity itself is pointing the way. Like footprints in snow, these icy objects trace the path of something heavy moving through the dark. Every new discovery adds a dot to the pattern, sharpening the outline of a ghostly presence. If we keep following it, the invisible might one day resolve into a faint point of light at the edge of a telescope's field, the long-lost ninth planet stepping out from the shadows. And if it isn't there, if the pattern dissolves with better data, that too will be a discovery. Because it will mean we've mapped the outer solar system more completely than ever before, turning uncertainty into knowledge. In science, even an empty sky can be full of answers. For now, astronomers continue to watch and wait, scanning the heavens where the clues seem to lead. They call this part of the search looking for a lantern in the snow. It's an image that fits perfectly. A faint light in a field of white noise, a glimmer just beyond sight. Whether that lantern belongs to a planet or simply to our own hope, it still guides us forward, step by step, through the frozen dark. Finding a planet that hides beyond the edge of sunlight is not a chase. It's a quiet ritual of repetition. You look, you measure, you wait. Then you look again. Out in the cold reaches beyond Neptune, nothing moves quickly. A single orbit might take 10,000 years, and from our vantage point on Earth, such a planet would crawl across the background stars at the pace of a drifting snowflake. If it exists, Planet 9 would not announce itself with a sudden flash, but with the subtlest motion, a dot that slides a fraction of a degree over many months. That is why the hunt for it feels more like meditation than exploration. Every observation is an act of patience. Astronomers gather stacks of images of the same patch of sky, separated by nights, then weeks, then seasons. Each image is overlaid with the others until a faint point reveals itself as moving while all the stars stand still. It's a little like noticing one dancer still swaying when the rest of the orchestra is frozen. The process begins with wide-field cameras, machines that can photograph huge portions of the sky at once, capturing hundreds of thousands of stars per frame. Each exposure lasts minutes. Sometimes, the total accumulated light represents hours of quiet waiting. When those exposures are compared, software searches for anything that has shifted even slightly. The shift may be measured not in degrees but in arcseconds, a term that sounds abstract but can be softened like this. An arcsecond is the width of a coin seen from 3 kilometers away. Planet 9, if real, would move by only a few of those each year. Because it is so faint, astronomers don't just rely on visible light. They turn to infrared, the warmth that objects emit, rather than the light they reflect. Even something as cold as -200 degrees Celsius still glows softly in infrared. This is how telescopes like NASA's Wide Field Infrared Survey Explorer or the future NEO Surveyor can detect worlds that look utterly black to human eyes. They sense heat as a kind of whisper in the dark. It's easy to imagine this work as high-tech wizardry, but at its heart, it's simply the art of noticing change. Once upon a time, this was done by eye, with astronomers flipping photographic plates back and forth under magnifiers, watching for movement between the stars. Clyde Tombaugh discovered Pluto that way in 1930, spotting the tiniest motion on 2 plates taken days apart. Now, computers do the flipping, but the principle is the same: patient comparison. If Planet 9 exists, it might appear first not as a bright discovery, but as a suspicion, a smudge that won't go away after the noise is cleared. Teams would reobserve, cross-check with other telescopes, and model how its orbit might fit the existing gravitational puzzle of the Kuiper belt. If those calculations align, the next step would be to predict where it should move next, then look again. Bit by bit, the invisible becomes a faint trace, and the trace becomes a world. At the Subaru telescope in Hawaii, one of the largest optical eyes on Earth, this search continues night after night. From atop Mauna Kea, far above the clouds, its wide-field camera scans the southern sky, where models suggest the planet may dwell. In a few years, it will be joined by the Vera Rubin Observatory, whose vast mirror will sweep the sky every few nights, creating an ever-growing movie of the heavens. Rubin's cameras will be so sensitive that they could detect a candle flame from thousands of kilometers away. When Rubin comes online, the entire sky will become an experiment in time. Astronomers will compare frames the way one compares breaths, each slightly different, each part of a pattern too large to feel until you step back. Somewhere in that rhythm, if the planet is real, its slow heartbeat will appear. To find something so faint also requires a new kind of teamwork. Modern searches involve not just scientists, but volunteers from around the world. Projects on citizen science platforms invite anyone with an internet connection to examine real telescope images, flagging any dots that shift between frames. People who have never looked through a telescope are helping map the outer solar system from their living rooms. It's proof that discovery now belongs to everyone, not just to those standing on mountaintops. There's an emotional symmetry to it all. In the 19th century, Neptune was found by mathematics alone. Its position calculated from tiny wobbles in Uranus's orbit. The prediction was so precise that when astronomers pointed their telescopes, Neptune was almost exactly where the equation said it should be. That moment proved that invisible forces could be followed to their sources. The search for Planet 9 is built on the same idea, but with better instruments and a larger sense of wonder. We are tracing the small, consistent tugs of gravity, like following ripples on frozen water back to the stone that started them. And if the ripples lead nowhere, if the pattern dissolves with better data, that's not failure either. Science often advances by subtraction. Every region of sky we can rule out brings us closer to knowing how our solar system truly formed. Maybe there is no giant planet out there at all. Maybe the orbits of those icy bodies are shaped by something else. The gentle collective pull of millions of small objects, or even the lingering influence of the galactic tide, the soft, faraway gravity of the Milky Way itself. Yet even that possibility keeps the search worthwhile, because every frame captured, every night spent scanning the outer dark adds to our map of the unknown. The edge of the solar system is no longer an empty border, it's a landscape waiting for its first explorers. Picture it, an astronomer alone in a control room, screens glowing softly, the dome of the telescope opening to the stars. Outside, frost gathers on the metal railing. Somewhere in that vast sky, a tiny point may be moving. A lantern in a blizzard of stars. They won't find it tonight, or maybe even this decade. But they will keep looking, frame after frame, year after year, trusting that persistence itself is a kind of light. Because in truth, what they are really searching for isn't just a planet, it's connection. The knowledge that even the most distant corners of the solar system still belong to the same story, still respond to the same laws. Whether or not the lantern is ever found, the search reminds us that curiosity is its own form of illumination. And perhaps that is what makes this pursuit so deeply human. The belief that if we keep watching long enough, even the coldest, faintest light will eventually reveal itself. In that faith, the darkness becomes a little less dark, and the waiting becomes part of the wonder. Every age of discovery begins with a new way of listening. For the sailors of the ancient world, it was the feel of wind in the sails and the shift of stars above the horizon. For the scientists of today, it's the whisper of light from across the universe, the soft pulse of data that tells us what exists, what's moving, and what might yet be hiding. In this moment in history, our new tools of listening and looking are taking shape, and they promise to change not only what we know about the universe, but how gently we learn from it. The next decade of exploration is already humming quietly into existence. Far above the deserts of Chile, the Vera Rubin Observatory prepares for its first night of full operation. When its great mirror opens, it will not stare at one small patch of sky, but sweep across nearly the entire visible dome every few nights. Think of it as a living diary of the cosmos written in frames of light. Each image will reveal millions of stars and galaxies, and when compared night after night, those images will show how the sky moves, how small things shift, how new lights appear and fade. For the first time, we'll see the universe not as a static photograph, but as a film unfolding in real time. Somewhere in that stream of images, an interstellar visitor like Oumuamua might flicker across the field, a faint streak appearing in one frame then gone in the next. The observatory's software will notice. It will alert astronomers before the object slips too far to reach. The hope is that, one day, a spacecraft will be ready and waiting, built for quick departure, able to intercept such a traveller before it vanishes into the dark. Elsewhere, NASA's NEO Surveyor mission is being assembled with a different kind of sight. Unlike Rubin's mirror, which looks at visible light, NEO Surveyor will watch in infrared, the glow of warmth rather than brightness. This gentle sense allows it to detect even the darkest bodies. Asteroids too black to reflect sunlight, comets wrapped in dust or hidden fragments moving silently through the inner solar system. It will help protect Earth from potential hazards, yes, but it will also extend our awareness of the quiet traffic that surrounds our planet, the unseen neighbours passing by, and out beyond our moon's orbit, the European Space Agency's Comet Interceptor will wait in stillness, poised at a gravitational balance point where the pull of the Sun and Earth cancel each other. From that peaceful perch, it will bide its time until something new, an untouched comet, or perhaps an interstellar object, appears on a path toward the Sun. When it does, the interceptor will awaken, springing into motion. Small probes will detach and fly alongside the visitor, tasting its gases, photographing its surface, reading its secrets before sunlight alters them. It's a kind of patience built into machinery, a human virtue encoded in metal. These are not instruments of conquest, but of empathy, designed to meet the unknown halfway. Further out still, on the plains of South Africa and the deserts of Australia, another instrument is rising, the Square Kilometre Array. When completed, it will be the largest radio observatory on Earth, a vast network of dishes spread across continents, all listening together. Their combined surface area will equal a square kilometre, yet their sensitivity will be so fine they could detect a cell phone signal from planets around nearby stars. This network will hear the universe's faintest murmurs, the birth cries of galaxies, the subtle rhythm of pulsars, perhaps even the deliberate tone of another civilization's transmitter if one ever points our way. In parallel, a smaller but equally ambitious project called Cosmic is testing what it means to multitask on a cosmic scale. Instead of dedicating whole telescopes to the search for alien technology, Cosmic listens while other science is happening. It piggybacks on radio observations of galaxies and quasars, quietly scanning for narrow artificial-like tones in the background. This way, the search for other minds becomes not a separate mission, but a companion to everything else we study, woven seamlessly into the fabric of exploration. Even our instruments for weather and communication are joining in. Satellites orbiting Earth now record atmospheric flashes that may finally reveal more about ball lightning and other rare plasma events. High-speed cameras aboard planes have begun to capture the transient blue jets and red sprites that dance above thunderstorms, proof that even the skies we thought we knew are still capable of surprise. All of these projects share something simple but profound. kindness in curiosity. They don't demand answers, they invite them. They acknowledge that knowledge grows best in open light, not behind closed doors. The scientists who build these machines understand that what they are really constructing is not just data pipelines or mirrors, but relationships with each other, with nature, and with time itself. What we are witnessing is the universe becoming self-aware through our collective patience. Every photon caught by Rubin, every faint pulse recorded by the Square Kilometre Array, every speck of dust sampled by Comet Interceptor adds a note to the same cosmic symphony. The melody is slow, nearly imperceptible, but it's there, a song of understanding stretching across centuries, and yet, even with all this power and precision, we remain small, looking out from a single world of oceans and air. Perhaps that's what keeps our science human. We can build machines that see farther and hear better than we ever could, but what they bring back still has to be interpreted by eyes that tear and hearts that hope. Each new discovery is, in some way, a reflection of ourselves, a mirror not only of what is out there but of what we're becoming inside. So when we talk about better ears and kinder eyes, we're also talking about us, about learning to observe without haste, to measure without arrogance, to share without fear, to treat the universe not as a puzzle to be conquered, but as a companion whose language we're only just beginning to understand. Perhaps that's why the work feels peaceful even in its enormity. The people at the observatories often speak softly, even during moments of discovery. They know that every light they capture has been travelling for unimaginable spans of time, thousands, millions, sometimes billions of years. To witness it now is like catching the end of a story begun before humanity existed. How can you not be quiet in the presence of that? And as we close this long journey, through comets that breathe without tails, skies alive with unexplained light, signals that almost said hello, and planets that may or may not be there, remember that science itself is a form of listening. Every hypothesis, every test, every recalibration is just another way of saying, we're here, we're paying attention. The mysteries we've explored tonight are far from resolved. Some may take generations to answer, but that's the beauty of it. The universe will wait. It has all the time in the world, and so in our own small way do we. So let the night settle. The telescopes are still turning, their mirrors catching light older than any dream. The data flows quietly, like rivers of numbers beneath the stars. Somewhere, a scientist yawns and smiles, watching a signal drift into clarity. The universe keeps its rhythm, and we keep listening. Sleep now, if you like. The cosmos is awake, keeping watch.